Hello, everyone. Let's just give it a minute so folks can join. All right. It looks like we've reached a steady state. So it's my pleasure to welcome everyone to the RC from Space webinar series. And today we're going to hear from Felix Vivant, who's going to talk about very interesting RC interactions at submesoscale. So take it away, Felix.
Yeah, thank you very much for being here at this seminar, during which I'm going to present the work we've done for the last 9 months. So yeah, I'm a master's student at the ENS Paris-Saclay, and I have visited Leah Siegelman, which is just here actually. You can say hi. And we worked in close collaboration with Patrice Klein and Hector Torres to investigate the influence of oceanic submesoscale fronts on convection within atmospheric storms, so at mid-latitude. And to do so, we analyzed the high-resolution couple model developed by Dimitris Menemelis and Andrea Molod. And this model was actually presented 2 weeks ago by Luna during the same seminar. So to introduce the oceanic fine scale I'm going to talk about, this is an image from the Suomi and NP satellite. So it was captured in the Southern Ocean, so between Antarctica and South America. And so we can so it captures phytoplankton blooms, and we can identify different scales in the ocean. So here mesoscale eddies of about 200 kilometers, but also finer scales such as submesoscale fronts with typical size of tens of kilometers. And these submesoscale fronts have a typical time of a few days or a week, which is the same time scale as storms, so the same time scale as the lifetime of storms. And so if we want to study the interactions between submesoscale fronts and storms, we need to resolve at the same time the ocean and the atmosphere, and also at high resolution, so at least 10 kilometers. So this is the couple model we use. So it was conducted in the framework of the Diamond project. So it's an international project. And this model consists of GEOS5 for the atmosphere, so 6.9 kilometers horizontal resolution. So it's a non-hydrostatic model. For the ocean, it's the MIT GCM, so 2 kilometers to 4 kilometer resolution.
Recording in progress.
And both models are. Sorry about that. Okay. So there is a feedback. Just wait 1 minute. Is it good?
Yep.
Okay. Yeah, so I was just saying that the model consists of GEOS5 and the MIT GCM. And so both models are coupled every 45 seconds and integrated as well. And the high resolution of both models allows to accurately modelize submesoscale in the ocean, but also fine scales in the atmosphere. And the fact they have both the same resolution, it allows to accurately modelize the interaction between fine scale in the ocean and in the atmosphere. So this is a global model, as you can see in this movie, of latent heat flux. So latent heat flux measures the transfer of energy between the ocean and the atmosphere. So from the ocean to the atmosphere due to the evaporation of water. And those fluxes are really important for weather at mid-latitude, because it drives convection, so cloud formation and all the moisture processes. And so if we look at the winter, so we are actually currently in December, so in the winter in the northern hemisphere. And so these fluxes are especially important above western boundary currents, so such as the Kuroshio extension and the Gulf Stream, mainly because of the cyclogenesis. So you can see storms, for instance, in the Kuroshio extension, storms developing from Japan to Western America, so above the Kuroshio extension. And the fluxes are particularly important when dry and cold air parcels are advected from the north. So as you can see here, because it creates a high air-sea contrast, so resulting in high fluxes. And these fluxes are really important for weather. And in addition to this atmospheric variability, we can also observe on the background the ocean. So we can see mesoscale eddies, barely see submesoscale fronts, but I'm going to introduce the submesoscale fronts in this couple model in a few minutes. So the literature has studied the interaction between storms and western boundary currents and mesoscale eddies. So for instance, by this analysis of Fusa et al., so they used a regional model, 18-kilometer resolution, and forced by a steady SST field. So an atmospheric model forced by a steady SST field. This field contains a large-scale zonally symmetric part, so basically cold water in the north and warm water in the south, and mesoscale eddies as well, so with size of typically 200 kilometers. And so they studied the response of storms above those eddies. So you can see a storm here. There are two different regions that we can identify, the cold sector. So as I said, there is the advection of cold and dry air above warm SST, so it creates high surface fluxes. We can also identify the warm sector, so the wind is blowing from the south, and so that creates the air-sea contrast is weaker than in the cold sector, so low fluxes. And in addition to that, we can also observe a strong correlation of surface fluxes by the oceanic mesoscale. So you can see a cold eddy here and a warm eddy here. And what they shown is that the amplification of air-sea fluxes due to the mesoscale increased convective heating, so convection, and so latent heat release. And this induced a polar shift of the storm tracks of about 500 kilometers. So it is known that mesoscale in the ocean strongly influence storms at mid-latitude. And mainly because they influence the hydrological cycle within a storm track. So this is a schematic of a storm track. So you can see two low pressure, so two storms. On this snapshot here, you can see also the same situation, so two low pressure. We can identify the cold sector and the warm sector that I just mentioned before. So here we can see high fluxes, so the cold sector. Low fluxes here, so the warm sector. And those storms are characterized by strong vertical motion within the entire troposphere because they are described by the physics of baroclinic instabilities. And so first, in the cold conveyor belt here, there is the advection of cold and dry air from the upper troposphere to the surface, resulting in high latent heat flux at the surface. And this additional moisture provided by the ocean acts as a preconditioning for the following storms, and mainly the diabatic processes occurring within the warm conveyor belt. So within the warm conveyor belt, there is the advection, the rapid rise of warm and moist air parcels that condensate into liquid and ice. And so it results in cloud formation, precipitation, and the influence of western boundary current on this hydrological cycle is known to intensify this hydrological cycle, and so the storm track. So as I said, all of this is relatively well understood for western boundary currents, so large-scale SST distribution and oceanic mesoscale, as I presented with this study of Fusa et al. However, it is not for submesoscale fronts, mainly due to the lack of high-resolution couple model that resolve at the same time fine scale in the ocean and fine scale in the atmosphere. And so the aim of our the aim of our research is to investigate that. So to do so, we extracted 3 months of winter data, so from the global model. So you can see Japan here. So we extracted this domain in blue right here. So on this panel, you can see the sea surface temperature. The black arrows are the surface wind in all panels. On this panel, it's the latent heat flux. The black contours are the sea surface temperature. So you can see mesoscale eddies with size of about hundreds of kilometers. They typically persist over a month. On this plot here, it's the Rossby number, so defined as the relative vorticity at the ocean surface divided by the Coriolis frequency. And so it allows to identify whether we consider submesoscale or not. So as we can see, the Rossby number here reach 1. So it means that we are observing and studying submesoscale fonts. So those submesoscale fonts have a typical size of 10 kilometers and persist over a few days, a week, as I said before. The atmosphere is way faster. So you can see on this panel, storms crossing the domain of study within a day. So they have a typical size of 1,000 kilometers. So it corresponds to the synoptic scale. And in addition to this synoptic scale in the atmosphere, we can also observe on this panel just here, smaller scales and faster scales. So characterized by pronounced surface wind divergence. And so they are typically clouds, squall lines, and so characterized by vertical velocities and precipitations. And as you can see, all those scales have an imprint on latent heat flux. So we can see an enhancement over warm eddies and also variations depending on the wind direction. And we can also see sometimes fronts corresponding to high surface wind divergence. And in order to quantify the respective contribution of these scales on the variability of latent heat flux, we performed a spectral analysis, so frequency wave number spectral analysis, and we divided the phase space into 4 subsets corresponding to the 4 scales I mentioned before, so oceanic mesoscale, submesoscale, and also atmospheric synoptic scale at high frequencies. So this is the spectrum of sea surface temperature. So as you can see, the percentage here are the percentage of the variance within each subset. So we computed that by just integrating the variance within a given subset and then divided by the total variance within the entire phase space. And so as you can see, the SST in our simulation is mostly driven by the mesoscale and to a lesser extent by the submesoscale. If we look at latent heat flux, we can clearly see the imprint of the ocean on moisture fluxes at the surface. So it corresponds to 50% of its variability. So 40%, approximately 40% to the oceanic mesoscale and 10% to the submesoscale. The other 50% corresponds to the atmosphere, so at higher frequency. So most of it is attributed to the synoptic scale. And this is consistent with the movie. So we saw strong modulation by cold sector and warm sectors. And if you look at the correlation in the spectral space, so this is a co-spectrum, so it indicates the correlation in the spectral space. We see a positive correlation, so it means that latent heat flux are amplified over warm SSTs and so warm eddies. And so all of this is consistent with the movie I just presented before. So this is as the surface. We shown that there is a strong impact of the ocean and oceanic fine scale on surface moisture and moisture fluxes at the surface. But now we want to study the response over all the troposphere. And so to do so, we performed 5-day averages to filter out most of this atmospheric variability and to study the response of the atmosphere due to the ocean. And we also studied the response, separately the response in the warm sector and in the cold sector, because as you will see, the responses are different. So to do so, we computed so over 5 days, we just select the frames when the wind is blowing from the south. And so that's what you can see on those plots. So since we removed most of the atmospheric variability, we can only see the modulation of latent heat flux due to oceanic mesoscale and submesoscale. So an enhancement over warm eddies, but also sharp gradients across submesoscale SST front. We can see kind of the same behavior for the planetary boundary layer height, so characterized by pronounced turbulence, so it's the mixing layer of the atmosphere, but also for the CAPE. So CAPE is the convective available potential energy. And so it measures so it's a vertically integrated quantity in the atmosphere, and it measures the energy available over all the air column for surface parcel to rise due to buoyancy force, and so moisture processes, convection, etc. And so it means that the energy available for convection is modulated by fine scales in the ocean. In addition to that, submesoscale fronts also induce surface wind divergence. So this mechanism is an effect of turbulence, which tend to accelerate the wind above the warm side of the SST front. So as you can see on this schematic of Shelton et al. And so depending on the wind direction, this mechanism creates easier wind divergence or wind convergence at the surface. And so it manifests as the positive correlation between the downwind SST gradient, so defined as the scalar product between the wind direction and the SST gradient, and the divergence. So here it's the wind stress divergence, but it is more or less similar to the surface wind divergence. And so here, since the wind is blowing from the south, we mostly observe in the warm sector negative wind divergence, and so surface convergence. And if we look at the magnitudes, we can see that the magnitude we observe at the submesoscale are greater than the one observed by Shelton et al. in 2004. So they used quicksat measurements, and so they observe mesoscale anomalies. And so this is consistent with a previous study performed by Strobach et al. So they used the same model I'm presenting right now, and they found that the same correlation as it was found by Shelton et al., for instance. So the same mechanism are valid for the mesoscale and the submesoscale, but we observe greater magnitude at the submesoscale. So you can see the gray areas here corresponds to the range of Shelton et al. And so greater SST gradient means greater surface divergence. And this surface convergence is associated with moisture flux convergence. So this moisture flux convergence is defined as follows, and is similar to the product of humidity and surface wind convergence. And so it means that above submesoscale fronts, there is convergence, so accumulation of moisture. And this is associated with vertical transport of moisture through the continuity equation. So for the moment, we're still at the surface, excepted for the CAPE. But now we want to look at the response in terms of convection above the planetary boundary layer. And so those three plots are outputs from the convective parametrization. So you can see convective mass flux at 3 kilometers, so above the planetary boundary layer, which has a height of typically 1,500 kilometers. So convective mass flux corresponds to the air mass within a convective cell. So it's a vertical mass flux. And so you can see at 3 kilometers that it's clearly enhanced above the SST front, the submesoscale front. This is associated with convective diabatic heating, so at 3 kilometers as well. So convective heating due to the phase transition of water within the convective cells. And this is associated at the surface with an enhancement of convective precipitation, so of about 2 millimeters per day. And this response is not a steady response, because if we look at the root mean square, we observe magnitude 4 times greater than the mean. So for instance, we compare, so for convective precipitation, we observe 40 millimeters per day compared to 12 for the mean. And so it means that atmospheric cells quickly react to the intermittent wind blowing over submesoscale fronts. It's not a steady response over 5 days where we observe a steady enhancement of convection. It's an intermittent one. And if you look at the vertical extension of this enhancement, so this plot corresponds to this section, so this meridional cross section. The white star here is the location of the submesoscale front. So you can see in black on this panel the SST in black, so the front. Associated with that, we can observe the modulation of latent heat flux, but also the modulation of CAPE in green. In terms of momentum, we observe the correlation as well with the downwind SST gradient in black and the surface wind divergence in red, creating positive vertical velocities in blue. And all of this induce a response in terms of convection. So within a narrow band of 30 kilometers, so horizontally, and which extend vertically from the Earth interface to half the troposphere, so 4 kilometers. And so if we want an order of magnitude of the vertical velocities associated with the convective mass flux, we can divide by the density of air, so which is approximately 1, and we found velocities of about 3 kilometers per day. And so at the surface, we observe also a clear enhancement of convective precipitations of 40 millimeters per day. And so this enhancement is quite significant if we compare to what has been observed for mesoscale anomalies. So this analysis performed by Putrasahan et al., they used a couple model at 25 kilometers resolution. So they resolve mesoscale anomalies. So you can see in red the sea surface temperature. So mesoscale anomalies. Above gradients, we observe anomalies in vertical velocities. So it's in pressure coordinates. So negative corresponds to upward motion. And so associated with this vertical velocity, we also observe, they also observed precipitation anomalies of about 1 millimeter per day. So 10 times weaker than what we observe at the mesoscale, even though it's the same physical and the same mechanisms. So the precipitation are greater and the horizontal extension is smaller as well. And so to conclude on the study of the warm sector, we found that the energy, so latent heat flux and the convective available potential energy is modulated by oceanic fine scales. We also found that the submesoscale front induce moisture flux convergence localized just above submesoscale fronts. And so this results in a clear enhancement of convection above these submesoscale fronts, and this from the surface to half the troposphere. And this response occurs also at high frequency, as we saw with the root mean square. So now the cold sector, so now the wind is blowing from the north. And so as you can see, latent heat flux are greater because the Earth-sea contrast is greater. So the cold sector really participates to pump moisture out of the ocean. But since the wind is blowing from the north, so in the other direction compared to the warm sector, we mostly observe moisture flux divergence at the surface. Sometimes we observe convergence, but as you can see on in the response in terms of convection, even for the region with moisture flux convergence, the magnitudes are weaker. So for the warm sector, it's 3,000, so compared to 1,000 here. And if you look at the convective precipitation, it's nearly equal to 0. So the cold sector participates to pump moisture due to high latent heat flux. But the cold sector has a weaker potential for convection because there is cold and dry air within this region. And also because of the wind direction, it mostly creates surface wind divergence and so downdraft. And if we compare the vertical extension of the warm sector and the cold sector, we see a counterwise secondary circulation. So due to the surface wind divergence in the cold sector, we can see a slight enhancement of vertical velocity above the warm side of the SST front, resulting in associated with a slight enhancement of convective activity, but the magnitude of convective precipitation are not equal to 0. And so this result suggests also two different positive feedbacks. So the first one in the cold sector, since we observe vertical motion from the upper troposphere to the surface, it suggests that it advects cold and dry air from the upper troposphere above the warm side of the SST front, and this enhance even greater the latent heat flux. In the warm sector, the vertical velocities induced by the amplification of convection can bring moisture, even more moisture, from the surface to the upper troposphere. And so to conclude on the findings, we first quantified the respective contributions of the atmosphere and the ocean on latent heat flux. So through the spectral analysis, so 50% for the atmosphere, 40% for the mesoscale, and 10% for the submesoscale. We also identified two different responses in the cold sector and in the warm sector. So as you can see on this schematic, the cold sector mostly participate to pump moisture because of high RC contrast and so high fluxes. And in the warm sector, even though the latent heat flux are weaker, the surface wind convergence and the moisture flux convergence at the surface is able to amplify convective activity, so cloud formation and precipitations. And so in addition to this local response of the storm track, so above the Kuroshio extension, we can expect potential influence on far-reaching weather, such as atmospheric rivers, as it was observed for the mesoscale. So for instance, by the study of Cheng et al., so they compared two climate simulations. So a high resolution one, so 27 kilometers in the atmosphere, 11 in the ocean, and a low resolution one, so 27 so the same resolution in the atmosphere, but a resolution 10 times lower in the ocean. So those three plots are the high resolution one, and this one the low resolution. So on this panel here, you can see the integrated water vapor transport. So it means that within the storm tracks, moisture is advected from Japan to Western America. We can observe the associated precipitation. And if we look at the west coast of America here, so this panel here is a zoom over the west coast. When moisture face mountainous region, they rise, and so they condensate into liquid and ice, and this results in precipitation. And if you don't resolve the mesoscale, they found that you don't accurately describe and represent such atmospheric rivers. And in particular, Liu et al. Shown that 30% of heavy precipitation over mountainous region are due to mesoscale eddies in the ocean. And so since their run does not resolve the submesoscale, and we found in our study that submesoscale fronts clearly modulate the hydrological cycle within the storm tract, we can wonder what about the submesoscale. So in other words, like, can the mechanism I described in this talk influence such atmospheric rivers? Thank you very much.
Thank you very much, Felix, for a great and interesting talk. The floor is open for questions. You can raise your hand or ask out in the chat. Do we have questions? Oh, Roger.
Yeah, thanks, Felix, for very interesting talk. That's quite an amazing analysis. A lot of work there. And I guess one thing I'm wondering is, to what extent is in the high resolution model, are these fluxes sort of squeezed into the smaller scales? And to what extent is there actually an enhancement of the mean fluxes when you resolve those scales? Were you able to address that at all?
You mean to compare two different runs?
I'm sorry?
You mean comparing two different runs with two different resolutions?
Well, I can imagine different ways of doing it, but I just wonder, on the one hand, you could say, well, it's really the larger scale mesoscale convergence, say, that controls the vertical transport. And so if you resolve the smaller scales, then that same mesoscale convergence gets squeezed into smaller scales and you see more of it at that scale. Or you could say, well, when you have those smaller scales, you actually get a stronger convective response because you resolve, it becomes effectively able to penetrate farther into the atmosphere because it's at smaller scale and more concentrated. And so I'm wondering if you were able to explore that distinction at all.
I think one answer is okay. Just show this. Not sure I understood your question, but you're saying that we observe the same physical mechanism for the mesoscale and the submesoscale, I guess. And so, yeah, indeed, we observe a stronger response compared to what has been observed at the mesoscale. But I'm not sure this. Sorry. Oh, okay, all right. Sorry about that. Okay, so maybe it might answer your response. So this is the same plot as I presented, but for a 2 months average. And so when we average submesoscale fonts over 2 months, at the end we end up with a mean state and mean SST fonts with a size of about 100 kilometers, or yeah, a bit more than 100 kilometers. So basically we can call that mesoscale. But at the end, it's maybe the sense of, I mean, the meaning of your question. At the end, since the processes I described are nonlinear, even though we observe same patterns at larger scale, at the end, like frame by frame, it's submesoscale fonts acting and amplifying the convection. And so as you can see here, for the 2 months mean, we observe precipitation anomaly of 4 to 5. And if we compare to another run, so the one I just showed previously of Putra-Sahan, at the end, the horizontal extension is the same as the 2 months mean I just showed you, but the precipitation are greater if you consider submesoscale, integrated submesoscale effects. Does that answer your question?
Yes, I think so. That's really very interesting. Thank you.
You're welcome. Thanks for the question.
Do you have more questions?
I can take one. I'm in the car driving, so I'm sorry, it's maybe not very coherent,
No problem,
and I haven't seen all the I haven't seen all the plots perfectly. But as an observationalist, I was wondering how you might use this information to plan a field campaign that looks at the ocean atmospheric coupling, from a vessel or from other instrumentation. I mean, maybe I know you're not so familiar compared to the model, but could you start to disentangle this coupling beyond the mesoscale from observations?
There is the SWOT mission first. So SWOT mission will probably allow us to for instance study the wind divergence at the surface above fine scale fonts. But I'm not very informed about the measurements possible for instance quantifying the convective response in terms of precipitation, for instance. I can't really answer this question because I don't have a lot of information on different campaigns and things like that. Yeah. Patrice just gave me the answer. So yeah, there is also another paper of Yang et al. They also used high resolution data, and they also find so they study like kind of the same case as the coal sector here, and so they found such an enhancement just above the planetary boundary layer, so above the one side of the SST for northwards wind, but they haven't observed this convective process. I mean, they haven't studied. They didn't study it. Does that answer your question?
Yeah, thanks. Could you repeat that paper you mentioned, and what do you know what observations they were using to look at this?
Yeah, I can write it just here.
Okay, thanks so much. Thanks for a great talk.
Thank you.
All right, Mohamed.
Hello.
So
Yeah, very nice talk. I have two questions by now. Let's start with the easier one. So are we doomed? So do we have to resolve the submesoscale all the time? Otherwise, our models are wrong. What makes you so confident that you have to resolve the submesoscale? I mean, for the mesoscale, I think there are plausible arguments, but how much do you have to resolve the submesoscale, and how much do you resolve the submesoscale in the model you used?
So I guess your question is related, for instance, with storm intensities and the atmospheric rivers I mentioned before. I mean, at the end of the talk, I guess.
Yes.
Is the processes I described have an impact on weather at large scale? I guess it's your question.
Yes.
So actually, I don't know. So the best for me, the possibility to study that is to perform sensibility experiments. So for instance, using a regional model, a couple one, and then you can initialize it with high resolution in the ocean, low resolution in the atmosphere, and it could be very interesting to see, such as this paper, if we can see a difference between the simulation who resolve submesoscale and mesoscale. And so to which extent we resolve the submesoscale in the model, I'm not, because I'm not an oceanographer. So maybe my answer will not be that precise, but by looking at other paper with higher resolution, for instance, at the MIT GCM, sometimes we can observe also like higher and smaller scale features, for instance, submesoscale eddies. In this simulation, we observe mostly submesoscale forms. So yeah, not sure. Does that answer your question?
Yeah, I mean, just the experiment you propose, people would like to run, but you cannot run it. But you cannot run a global submesoscale ocean model with an atmosphere on top and look at large scale impacts, right? So what the CSM high resolution does is well, this one is pretty much the limit right now. So we have to be a little smarter than just resolving everything.
Yeah.
I think there's hope.
So for instance, find parametrizations and so something
Yes.
that can modelize such processes if they have an importance. But so that's basically the aim of my PhD, to run such a sensibility experiments to see if there is a response in terms of intensity, for instance, of storms, so mean sea level pressure and etc.
There's another comment that the model you uses the same parameterizations as you would use for a degree model resolution. It uses the same flux parameterizations, right? And they are kind of tuned to give you the right answer at low resolution. And if you then put it at a high resolution, you just trust Monty Novikov. I think that's what 90% of the community does, and that's good. But you could also ask what the validity of a high resolution model is with these parameterizations.
Yeah, so we probably will have answer with SWOT, because we're gonna have high resolution data, and so we could compare, for instance, the response in terms of wind divergence, and so the response in terms of wind divergence is related to the parametrization at the surface. So because without heat flux at the surface and so the Monod-Kubov similarity theory, so the wind stress parametrization, I guess you don't observe the mechanism I explained. So no,
there's hope. Yeah, I'm not sure if SWOT is the answer, but others have opinions on this.
Yeah, my knowledge is limited. for the moment, so I
Yeah,
cannot.
mine too.
Yeah.
Did you have a question, or Ad, you had your hand
Yes,
raised?
but I have to go. So
Oh, okay. Cool.
I was just going to say maybe shortly that several manuscripts show the connection between convective rain cells and spectrometer convergence and divergence. The spectrometers, you have direction, so you can compute convergence and divergence. If you do SWOT, I don't think can do that. So particularly for ASCAT, we see very clear connection between convection and the convergence, divergence, and curl at the surface. We have some students also working now on it, master students. So I can give you some reports to see for yourself, but we did not look into the specific mechanism that you mentioned. So I think there's still some work to do to link it to what you did. I think it's excellent what you did. So certainly very interesting. Thank you. I need to go now.
Okay. Thank you.
Felix, there is a question in the chat. Rick, I'm not
yeah.
sure if you want to ask away or.
Yeah, I can certainly read it. It's just a question about the airstream feeder mechanism. I think that Demirjian is referring to as well. And the question is whether the submesoscale affects the anticyclone, and or to what extent might it affect the anticyclone, because a more intense anticyclone presumably would be a good thing to bump into if you were a cyclone. You'd have an enhanced warm sector moisture convergence.
Yeah, but to be honest, I don't have an answer directly, but yeah, it could be interesting to study there is a paper who study that. So the moisture flux and the flux of energy between low pressure and high pressure at mid-latitude. And so I think they studied the response of the response of these fluxes to western boundary currents, and they found a different they found that the forcing by the ocean influenced the moisture transport between low pressure and high pressure, but they didn't study the fine scales in the ocean, and so currently I don't have a clear answer to your question, but it could be interesting to study that for sure.
Yeah, and the sensible heat flux is in there. It's somewhere in there. Is that in the question?
Oh yeah. So it's sensible X-flux have like this more or less the same variation of latent heat flux. The difference is that latent heat flux is most of the time greater. So that's why I mostly talked about latent heat flux.
Yeah, it was
and also yeah, go ahead. And also sensible heat flux are negative can be negative in the warm sector.
Yeah,
that's the difference.
Yeah, excellent focus. Thanks.
Thank you very much.
All right, do we have any more questions? Okay, if not, thanks Felix again for such a lovely talk and interesting discussion. And I'll see you all next week. Thank you, Felix.
Thank you very much.